All right, welcome back. This is another requested video. This video request comes from Australia, so thank you very much for the request. And this is just another one of those structure determination problems. I've got a variety of spectra, UV vis, IR, NMR, so we've got some nice looking NMR data here that we're going to take a look at. We've also got a mass spec that we're going to take a look at. So we've got a variety of spectra, and we're supposed to come up with a plausible structure for this chemical compound. So let's go ahead and get started. The first thing I'm going to do is talk about this UV vis, and the way that I'm going to talk about it is just by going like this. I don't know that much about UV vis. I don't find it to be that useful. So if you do find something that's useful in that UV vis, great. I'm just going to skip right ahead to the IR. I'll talk about all the other, I'm not going to just skip over everything, but I will talk about all the other spectra that were given. But that UV vis just to me is not really useful, probably because I don't really know what it says. Anyhow, the IR, I do know what it says, and I can talk about that. So the first thing that really jumps out at me when we're looking at IR for the first time, we want to sort of look at the really obvious things first. We want to say, this is really obvious. I know for sure this information, and I know for sure that this is a C-double-bond-O. I know this is a carbonyl-carbon oxygen stretch. I'm going to estimate the wave number here at 1710. And that's really obvious to me. It just really jumps out. You know, I think that for sure that's indicative of a C-double-bond-O. So I think that we can label that. Right next to that here, we've clearly got an aromatic benzene ring. You know, this 1600, that is very indicative of this aromatic ring. So I think that that's a good, a good starting point. Over here, we've got sp3 CH bonds. So right below 3000, and then right above 3000, sp2 CH bonds. If you have any practice with IR, especially if you're taking organic chemistry right now, I think you're getting really familiar with these sp3 hybridized CH and sp2 hybridized CH. Right below 3000, you see this nice cutoff here. So very clearly sp3 hybridized CH bonds over here. And then we do have sp2 hybridized CH as well. So those four things, those are the really obvious things that I for sure know are part of my structure here. This little peak here, I was sort of wondering about it, this little spike here that's at maybe like 3200 maybe or so, 3400. I'm not sure if that's something we really need to worry about, and at this point in time, I'm going to ignore it, right? I'm only going to focus on things that I really know for sure, and I really know for sure these four things. Okay, moving right along to the mass spec. So the mass spec is something that we're going to use more to check once we have a plausible structure. So we're going to come back to most of this in just a minute. But right away, I see that we're given a chemical formula. So it's always good to have in the back of your mind. And right away, the first thing that jumps out at me is O2. So when I think about this O2, the ways that we're going to get O2 into our, or I guess we should say 2 oxygen atoms into our structure, is either we've got a ketone or aldehyde here and an alcohol, which we don't, because if it was an alcohol or a carboxylic acid, we would see that in our IR. An alcohol would give a broad shift here, broad peak here. A carboxylic acid would give a really broad, peak here. So we can rule out alcohols, we can rule out carboxylic acids. So in my mind, the thing I'm thinking of at this point in time is an ester. If I have an ester, then that would give me my C-double-bond-O. It would give me 2 sources of oxygen atoms. So that's what I've got in my mind at this point in time. But still preliminary, so we're not going to be drawing any conclusions yet. But I think having that in the back of our mind is a good thing to have. All right, let's look at this NMR. So again, the IR and the NMR, I think those are the best starting points. Let's make sure we can see everything here. And looking at this NMR, again, the first thing I'm going to do is try to find things that really jump out at me, right? I think that oftentimes we're tempted to sort of solve everything at once, but we really need to sort of take it step by step and be as methodical as possible. So in the NMR, the thing that really jumps out at me first and foremost is this huge doublet. And anytime I see a huge doublet, to me, I'm thinking isopropyl group, because both of these CH3 groups, they'll be chemically equivalent, and so we would get one signal, and then to split it into this doublet, we would need a CH group there, and that's an isopropyl group. So this, I think, is very clearly what's going on in this region. Anytime you see this huge doublet, that's sort of what you should have in the back of your mind. And then this peak here would be this CH peak here. So the integration should be 1 to 6. That seems about right. I think this is a blow up of this peak here, and we should get 7 peaks. So I see 1, 2, 3, 4, 5, 6, 7. So that seems good, right? So we've got this CH linker here. Now this peak over here, this one I thought about for quite a little bit, because it should be CH2. So if I look at the integrations here, this would be 1. This looks like double. So I've got a CH2 group that's split into a doublet. So putting a CH2 group here makes a lot of sense. Oops, that should be a 2. CH2, got a little carried away there. Putting a CH2 group here makes a lot of sense because it would be, you know, a doublet because of this CH. But I'm a little concerned by the splitting, right? I would expect this CH to have more complex splitting because I would be splitting into a triplet here and then that septet from my CH3 groups. But it could be that it is, and it's just sort of overlapping. It could be that the coupling constant is the same or very similar. So I think that's okay, and I think at this point in time it's good. But now we need to have a reason why it's so far downfield, right? If we do have the CH2 group here, why is it so far downfield? Why is it at 4.1? To me, that's pretty obvious that it is bonded to an X group or an oxygen. So X meaning something very electronegative, pulling that electron density away, shifting it downfield. I know that I have oxygen because of my mass spec, so I think putting an oxygen here next to my CH2, that makes a lot of sense. So I think that this is a good sort of piece of the puzzle for our NMR data. I've got my CH2 or CH3s here, my isopropyl group, and then my CH2 linker here, which is bonded to oxygen, shifting it downfield. The CH here would split this to a doublet. So everything really makes sense. The only thing I'm a little bit hesitant about is the coupling of this CH. I might expect it to be a little bit more complicated. This is such a nice looking septet. You know, I'm a little hesitant because it should be split by the CH2 as well, but it could just be that it is, and the coupling is just sort of overlapping, and I think that's fine. Over here is an aromatic region, so here we're at 7.5 and 8. That's my aromatic region. I do have some symmetry here. The fact that we're seeing sort of 2 distinct peaks does suggest some sort of symmetry. So not too complicated, not just a big jumble. But at this point in time, there's not really much we can sort of assign just yet. I think we'll come back to that. All right, now I think it's time to sort of give it a go and make our first prediction. And again, when you're doing this, so at some point you sort of have to take the information that's given and come up with a structure. Just put something down and then sort of not really guess and check. I guess it's somewhat guess and check, but go for it, right? And then see how it fits. And if it doesn't fit, that's okay, right? We can fix it. We can come up with a new structure. But if it does fit, then that's good. That's what we're trying to do. So what I'm going to draw out is my first go. And the way that I came up with this is I thought about my benzene ring, and I thought about my C-double-bond-O. I had ester in my mind from before, and I started with that. And the fact that I have a 1710 shift for my C-double-bond-O, to me that really suggests I've got a conjugated C-double-bond-O. I've got a conjugated ester, because my table here says that esters should come at about 1735, but that conjugation is going to lower the frequency. So when I had to decide, right, where I'm going to place my benzene ring in relation to my ester, I figured it probably makes more sense to put it here so I could have conjugation lower the frequency of this C-double-bond-O. Now over here, I've got my other piece, right, from my NMR spectrum. I know that oxygen should be bonded to my CH2, CH, and then my isopropyl sort of group here. So this is my first guess, essentially. Now what I want to do is sort of go back through and make sure everything makes sense, make sure everything lines up. So C11H14O2, I can count my carbons and hydrogens here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. C11. H14, so I've got 3, 6, 7, 8, 9, and then I've got 5 on my benzene ring, my benzyl ring, so that's 14. And then O2. So right there, that matches up pretty good. Going back over through our IR and NMR, we should have sp2 and sp3 hybridized CHs, sp2, sp3, that seems good. I've got my C-double-bond-O, I've got my benzene ring, I've got conjugation that's lowering the frequency of my ester down just a little bit, that seems good. Over here, I've got my isopropyl group, that seems good. I've got my CH2 right here. Again, that seems good. All of this should be seeming good. Let's go ahead and talk about our mass spec. So this is now time for our confirmation, sort of. So if we look at our mass spec, this is our mass peak, and then I should be thinking about fragments that equal into these pieces over here. So the most obvious fragment for 77, something that you'll sort of get used to sort of seeing, is just a benzene ring. So that piece there, if you add that up, that equals a mass of 77, so that's a good fragment. The other fragment at 105, if you just add in, a CO, right? If you add CO to 77, you get 105. So this other fragment here, where I get a piece there, that is my 105 peak. Now this 122 peak, this took me a little bit of time, and I actually had to consult Roxy, my fellow organic chemist, to help me out with this, because what this peak ends up being, so when I drew it out, I was like, well, this is the fragment that we're seeing at 122. This is the fragment that is at 122, but how do we get that fragment? And there's actually a rearrangement that can occur where this oxygen actually gets protonated from this hydrogen here. So this sort of swings around. We can actually protonate, and then we can cleave. So it is the same fragment. It's just really sort of flipped. But this is a rearrangement and then a cleave to get to this fragment. So probably a better way to draw this would be that this gets protonated. This oxygen gets protonated from over here, and then we've got O cleave. So this is my fragment really that's at 122, and this is my whole mass fragment that we see here. So all of our fragments, those make sense, and I think that it's really, again, confirms, or maybe this is the way that we would have come up with these fragments in the first place, right? This is how we know that we've got that conjugated C-O because of my fragments here, right? This really suggests, this 105 really suggests that's where my C-O is. So that's a good confirmation. Now the last thing, I know this is a long video, but got to cover all the bases, is our DEPT. So our DEPT is going to, that's an oxygen, is going to tell us about our carbons. This is a carbon NMR, and the things that have pluses are CH3s or CHs. So in this region here, I've got CHs. So I've got, these two are going to be equivalent. So I've got 1, 2, 3 peaks that I should see over here. 1, 2, 3 peaks that are all CHs, so that's good. Here I've got a CH2. In my DEPT, it's saying that the things that are labeled with pluses are CH3s or CHs. The things that are labeled with a minus are CH2s. I've only got one CH2, so that's going to be right here. Now, in this region over here, I've got 2 more peaks. One should be a CH3, and one should be a CH, and that's what I see here and here. So I think that this looks good. If I wanted to go ahead and label these, we'll call these A's, B, C, D, D, E, and F. Then I would label this as A, B, C, excuse me. I don't know which one of these would be D or E, but we could call this D, E, and F. I think that makes sense. But D and E clearly could be switched. I'm not 100% sure on that, but I don't think it matters too much. We could do the same assignments up here for our proton NMR. I think clearly we've got A, B, C. We talked about those a little bit earlier. We can label it here A, B, and C. Now for our aromatic region, I think that these peaks here are D, right? So those are going to be here D, and then this all is E/F. D should be split into a nice doublet, so one signal split into a doublet from E, and I think that that's what we're seeing here. So I think that would be my assignment. I think that this is a good structure. I think we've put all the pieces together here. So this would be the structure that I propose. I think I like this structure. We've covered our bases for our IR, for our NMR, for our mass spec. Everything sort of makes sense. So I think this is good. All right, hopefully that is helpful. Let me know in the comments below if you have any questions or would like to request a video. Cheers.